Your feature matrix is 10,000 rows by 500 columns. Eigendecomposition requires a square matrix. SVD does not. Equals U times S times V transpose works for any matrix shape rectangular, square, wide, tall. U captures the row structure. V captures the column structure. S ranks every factor by importance. This one decomposition is behind Netflix recommendations, word embeddings, image compression, and anomaly detection in your monitoring infrastructure. The eigendecomposition we built in videos 12 and 13 is a special case of SVD for square symmetric matrices. Today we go general. For a matrix A with m rows and n columns, SVD produces U which is m by m and orthogonal, S which is m by n with singular values on the diagonal in descending order, and V-transpose which is n by n and orthogonal. The singular values in S are non-negative and are the square roots of the eigenvalues of a transpose A. That is the connection back to eigendecomposition. U columns are the left singular vectors, they span the row space. V rows are the right singular vectors, they span the column space. For a worked example with A being 4 by 3, we get U 4 by 4, S 4 by 3, V transpose 3 by 3. The rank of A equals the number of non-zero singular values. Key difference from eigendecomposition: eigendecomp needs equals a transpose. SVD works on any A. The connection is a transpose A equals V times S squared times V transpose, which is the eigendecomposition of a transpose A. Singular values squared equal eigenvalues of a transpose A. Truncated SVD keep only the top k singular triplets. Set AK equals U first k columns times diagonal S first k times V first k rows. This is the best rank k approximation of A by the Eckert-Young theorem. No other rank k matrix is closer in Frobenius or spectral norm. For economy SVD, parse full matrices equals false to get U as m by k instead of m by m. 4 applications. 1. Collaborative filtering. Decompose the user item rating matrix. U holds user latent factors. V holds item latent factors. S ranks their importance. Fill missing ratings by reconstructing from the top k factors. 2. LSA for NLP. SVD on the TF-IDF term document matrix reveals latent topics. Top k singular vectors capture semantic structure synonyms cluster together. 3. Image compression. A 1000 by 1000 image compressed to rank 50 stores 50 times 2001 values instead of 1 million, nearly 10 times smaller with visually acceptable quality. 4. For your 96,000 device monitoring network, stack metric time series into a matrix. SVD extracts the normal operational pattern. The residual after subtracting the low-rank reconstruction flags anomalous devices. 5 NumPy patterns. Full SVD, U, S, VT equals NP, linear_LG.SVD, A, full matrices equals true, gives the complete decomposition. Economy SVD, full matrices equals false, U is m by k not m by m, more efficient when you need the full U but not padding. Rank k reconstruction, use U first k times S first k times VT first k. Use broadcasting, U times S broadcast, at VT. Pseudo-inverse, NP, linear_LG, PINV, A, uses SVD internally, computing V times diagonal 1 over S times U transpose. Truncated SVD from scikit-learn for large sparse matrices without computing the full SVD first. 2 definitions to know cold. Singular values, non-negative diagonal entries of S, square roots of eigenvalues of a transpose A. Truncated SVD, keep top k singular triplets to get the best rank k approximation of A. Key rules, any matrix has an SVD. Orthogonality, U transpose U equals I and V transpose V equals I. Reconstruction error decreases as k increases. Use full matrices equals false for efficiency. 2 exercises. Compute SVD on random 100 by 20 data, plot singular values and reconstruction error versus k. For a 200 by 200 matrix, compute the compression ratio k times 2n plus 1 over n squared for k equals 5, 10, 20 and find the crossover point. You started with vectors and dot products and finished with SVD, the most powerful decomposition in data science. Drop your answer to the rectangle question in the comments. See you in video 15.